Thank you all for coming. This is the Kavli-sponsored session on frontiers in exoplanets research. I'm Brooks Hansen. I'm Executive Vice President at the American Geophysical Union, and my co-chair is Kim Unterborn from Arizona State University. We're really pleased to have a really fantastic set of speakers here today. This session kind of builds off a workshop we had last August, thanks to the support from the Kavli Foundation, to bring astronomers and astrophysicists and geophysicists, planetary science together to really look at the how to catalyze, how to energize, how to collaborate on the exciting new data theory modeling that we're getting around exoplanets, as well as exciting new observations in our own solar system and of our sun that help in both directions understand our solar system better and exoplanets better. And this session in large part was put together by some of the exciting topics we discussed there that will be, our data coming in right now from recently launched telescopes, as well as from the lab, as well as new data expected to come in as the James Webb Telescope becomes operational, as other exoplanet surveying telescopes become available. So it's a really exciting time. We're going to move in this session from kind of some of the laboratory challenges and needs in interpreting exoplanet atmospheres, and as well as atmospheres in our own solar system or other components of exoplanets, all the way to some early detections of magnetic fields in exoplanets and everything in between. So it's a really exciting lineup. Please stay at the end. We'll have a quick panel discussion to kind of explore some of the common themes that were raised by the talks after the last talk. And just a reminder that the Centennial programming tomorrow is called It Is Rocket Science. It's a whole day of Beyond Earth kind of general programming organized by our council. And tomorrow is the Beyond Earth neighborhood, so there'll be everything from solar physics to planetary science to solar system science to exoplanets. So a great session tomorrow as well for those that you want to learn more. So let's get started. I think we're right on time. So the first talk will be by Sarah Horst from Johns Hopkins University on exoplanet atmospheric modeling and experiments in the era of the JWST. Sarah.
I'm apparently shorter. Okay, there we go. So I'm going to start this session, which I think is really exciting, just by kind of putting us in a little bit of context of where we're at with exoplanets, and then I'm going to go through a laundry list of things that we need before we can figure out any of the questions that we're trying to answer, which is maybe an interesting way to frame a talk. We'll see how it goes. This one? Yes. Okay, good. So stepping way, way back, a bunch of the questions that planetary scientists are really interested in answering, and I think astronomers as well, are like some of the biggest questions I think that we tend to think about as human beings. Questions like, how did we get here? Are we alone? And one of the things that I'm really interested in is trying to understand what role atmospheres play in the origin of life, in the evolution of life, and also when we're thinking about exoplanets, in the detection of life, because that's where we're going to be able to really find those first hints of life. And so then the next question is, I'm an atmospheric chemist, and so why does atmospheric chemistry matter in trying to answer these questions? And the reason for that is that atmospheric chemistry really determines the chemical composition of the gases that you find in an atmosphere. This is really important for searching for things like biosignatures, for evidence of life in an atmosphere, whether that is an atmosphere in the solar system, looking for evidence of life in the Martian atmosphere, the atmosphere of Titan, or whether we're looking at the atmospheres of planets around other stars. The atmospheric chemistry also determines whether or not there are particles in the atmosphere. That also determines how many there are, what kind there are, and where they're located. That also really determines how radiation moves through an atmosphere. So the gases and the particles both determine which photons get deposited where in the atmosphere. That determines things like the temperature structure. And so that tells us a lot about what the surface temperature is going to be like. And really frustratingly, all of these things are actually related to each other. And so as the temperature changes, your reaction rates change, which change how easily gases get converted into particles, which then change where your photons get deposited, which then change your temperatures. And so it's a complicated system to try to understand. So then looking at exoplanets, it turns out there's lots of them. I downloaded this graphic last night, which the danger of talking about exoplanets is that you constantly have to update this plot, which is actually really exciting. But it looks like we have more than 4,000 confirmed exoplanets at this point, which is a lot of planets, honestly. And we're actually already able to characterize the atmospheres of some of these planets using tools that are already available, like the Spitzer Space Telescope and the Hubble Space Telescope. So we've already been able to measure things like atmospheric temperature, winds, clouds and hazes. We've found things in the atmospheres like water and methane, sodium and potassium. And so we're already able to characterize these atmospheres with the tools that we have available. And our ability to characterize these atmospheres is only going to increase with things like the James Webb Space Telescope and large ground-based telescope facilities coming online in the near future, hopefully, knock on wood. And so one of the things that's really interesting, though, about these planets is that they come in very different flavors than we see in the solar system. And so this plot here shows the period, the orbital period on the x-axis, so how long it takes the planet to orbit its parent star. And on the y-axis, in this particular case, we're looking at the mass in Jupiter masses. So those larger circles are giving you the context of the types of planets that we have in the solar system, which are well known. You can see Jupiter is sitting where it should be at 1 Jupiter mass, that large orange circle. And what you see when you look at this plot is so far, most of the planets that we have found are very different than the planets that we see in our solar system. We now know from the Kepler telescope that the most common planet in our galaxy is a type of planet that we do not have in our solar system. So it's a planet that's larger than Earth and smaller than Neptune. And so this is both exciting and frustrating as a planetary scientist, because it means that a lot of the work that we've done to understand solar system atmospheres, to understand how atmospheric processes work, can't just be immediately applied to these planets that we're finding around other stars. The flip side of that, of course, is that this provides us with the opportunity to actually test our understanding by looking at this phase space that we haven't actually been able to see before. The other thing that I want you to note, this is again orbital period on the x-axis, but now we're looking at the calculated temperature on the y-axis. So we actually only have a handful of measured temperatures for exoplanet atmospheres, but instead these are temperatures that have been calculated using something called the effective temperature. And you can see that there's a huge range of temperatures that we find should be possible, should be present for exoplanet atmospheres, ranging from the temperatures that we see in the solar system, the very cold temperatures of Pluto and Titan and Triton, 40 to 100 Kelvin, all the way up to many thousands of Kelvin are going to be present in these atmospheres. This is a huge temperature range. It's much, much bigger temperature range than is seen in the solar system, and this provides us with a lot of opportunities, but there are also a lot of challenges involved, which I'm going to mention in a second. We also know already that from a bunch of transiting exoplanet measurements that we see a broad range of atmospheric compositions and also the presence of particles. And so this is a really nice plot that just shows a number of planets that have already been studied with the Hubble Space Telescope. In some of them, we see the presence of water, we see sodium, we see potassium. In other ones, we see a slope that's very, very indicative of the phenomenon of Rayleigh scattering, indicating that there are particles in the atmospheres of these planets. And so we've already been able to characterize a little bit some of these planets, but we still have a lot of work that needs to be done. We also know that a lot of these planets that I mentioned, these ones that are larger than Earth and smaller than Neptune, have some type of aerosol absorber in their atmosphere. This is kind of the poster child of this problem, which is GJ1214b. This is, I think, one of the most precisely measured flat lines we have ever measured in astronomy, which took quite a large number of Hubble orbits to determine that there are no spectral features that can be seen in the Hubble data. And this is indicative of the fact that there are particles in this atmosphere that are muting the spectral features we would expect to see in an atmosphere. We don't actually know in the case of GJ1214b whether these are clouds or photochemically generated hazes or both, but we see this flatline spectrum in quite a few of the atmospheres that we've been able to characterize so far. This shouldn't be surprising. We know from the solar system that most atmospheres have some type of particle in them, but this is something that we're also going to have to confront as we start thinking about studying the atmospheres of planets around other stars. We also know that clouds of all kinds are going to be present in extrasolar planet atmospheres, and in particular things that we would never think of as clouds. So materials that are rock forming on Earth, things like olivine and pyroxene, are things that we can expect to find behaving as clouds in the atmospheres of a number of exoplanets. And so this means that we have to start thinking a lot more creatively about how clouds actually work in planetary atmospheres because of this phase space that we're going to be able to access that we can't currently study in the solar system. So if you want to look for life outside of the solar system, where do you look? The first thing that you will probably find out if you ask someone this question is that you want to look in the habitable zone. And we consider the habitable zone to be the region around a star where equilibrium temperatures allow liquid water to be stable on the surface of a planet. So this is going to be the first place that we're really focusing on for the search for life, because we believe that liquid water is, if not a requirement for life, certainly something that would help. It's important to emphasize at this point that a planet in the habitable zone may not be habitable. And just because it is habitable doesn't mean it is, was, or can ever be inhabited. So we have to be careful about our nomenclature. So if we're looking at planets in the habitable zone, what are we looking for? And when we're thinking about exoplanets, it's important to remember that at least for the foreseeable future, we are only doing remote sensing measurements. And so we are only able to look for the way that materials are interacting with light, whether that's the surface of the planet or the atmosphere of the planet. So one thing that we could look for is something suspicious in the atmospheric composition. So if you were looking at Earth's atmosphere, you might find the composition of our atmosphere suspicious. Our atmosphere is very strongly in disequilibrium because of life on Earth. And so if you were to see something suspicious in the atmospheric composition, that might be a sign of life. What is that? I mentioned disequilibrium. We talk a lot in these communities about biosignature molecules, although nobody can really agree what those molecules are. You could look for things like pollutants. We talk about things like technosignatures. If you could detect chlorofluorocarbons, you would have pretty good information that there is life on planet Earth. And so you're looking for something in the atmospheric composition that tells you that this is not a normal abiotic planet. That didn't do anything. So then how would you check? So we launch James Webb, we get these beautiful spectra back, we see all kinds of interesting molecules in these atmospheres, we start to have conversations about maybe this is the sign of life in the atmosphere of one of these planets. So how do we check? And the main way that we're able to check at this point is ruling out production by abiotic processes using models. Whether those are models of the atmosphere, whether those are models of the interior, exchange between those two places, which is very important. But that's really our main tool for checking, for ruling out these abiotic processes. So how do atmospheric chemistry models work? Well, this is an example of an atmospheric chemistry model that I'm extremely familiar with, although it's not an exoplanet model. This is an example from Titan. And the way that these models work is you have a whole bunch of inputs that you have to put into the model. You have something about the initial atmosphere, its composition, its temperature, and then you have to put in a whole bunch of extra information. Things like chemical reaction rate coefficients, things like photolysis cross-sections. You need to know something about the energy deposition. So what is the actual flux coming from that star? Are there other sources of energy to the top of that atmosphere? Things like energetic particles that could be coming into the top of the atmosphere. And then in each kind of layer of the atmosphere, you just calculate what the chemistry should be doing, what it's producing, what it's losing. You also have to think about transport, because winds can move materials in an atmosphere, dynamical processes transport material upward and downward, and so you have to think about that as well. And then you can output a final atmosphere and start the process over again. The reason that I wanted to show you this, though, is because I really want to emphasize that there is a lot of information that goes into these models that has to be measured in the laboratory or calculated from theoretical predictions. So things like reaction rate coefficients, things like photolysis cross-sections, those are things that come from the laboratory or from theoretical calculations. And without that information, it's very hard to actually believe the outputs of these models. And we don't, as you'll see in a minute, actually have most of this information for a lot of the exoplanet atmospheres that we're interested in studying. One second, sorry. So, the point being, to understand both the current exoplanet atmosphere observations that we already have, and also all of this amazing work that we're looking forward to in the future, we really need to do a lot more theoretical and experimental work. And so at relevant temperatures and pressures, we have a laundry list of things that we need. And I think one thing that's kind of frustrating to mention at this point is relevant temperatures and pressures when you're talking about exoplanets mean a huge phase space, much, much larger than anything we've ever had to deal with in the solar system. We need molecular opacity line lists, including broadening, and now we need them at high spectral resolution because we have these amazing tools coming online. There's an example of a whole bunch of these. Please don't feel the need to write these down, although you can feel free to take a picture of this slide because I'll show you a reference where all of this information exists. But you can see that we're basically missing, yeah, the last one's my favorite. We just need everything. Everything you could think of that can be volatile at any temperature up to like 2,000 or 3,000 Kelvin needs to be done, which is almost anything. So we need these really badly. There's also, a whole other list of things. I don't even know what some of these species are, to be completely honest, but they can be present in certain atmospheres. We need collision-induced absorption and dimer opacities. In particular, we need hydrogen and CO2. We also need to extend the temperature ranges for other existing measurements. So this is one of the other frustrations. In some cases, we actually already have the measurements for these specific things, but they don't go to a broad enough temperature range, or they're not measured at the right pressures. And so even the existing databases for a lot of these things just aren't complete enough for us to really be able to use them for exoplanets. That's the reference, which will, I think, disappear and then reappear. This slide got broken somehow. We also need laboratory cloud and haze formation studies, and this includes things like optical properties. So those particles in the atmosphere of GJ1214b, if we want to understand the impact that they have on the temperature structures of these planets, if we want to figure out how to model these atmospheres correctly, we need to know how those particles interact with light. And the main way to do this at this point are through laboratory studies of their optical properties. We also need photoabsorption cross-sections over a broad wavelength range because atmospheres interact with all different types of photons. We need broad wavelength ranges. We also need to expand and refine our chemical reaction rates, and that includes both products and branching ratios. So one of the problems you often run into in trying to model atmospheres is that people have either measured one or the other. So maybe we know the rate, but we don't know the products. Or maybe we know the products, but we don't know how fast the reaction happens. If we don't have both of those things, you can't actually input that in any particularly constructive way into the model. We also need vapor pressures, which sounds like a really simple thing, but we don't have them for a lot of the species that we're interested in, or again, we don't have them over the relevant temperature ranges. And so we might have them for Earth-relevant temperatures, but we don't have them to low enough temperatures or high enough temperatures to actually be able to input them into a lot of the modeling efforts that we're doing. This is particularly important for thinking about things like cloud formation. We also need heterogeneous reaction rates. So this is something that the Earth community is far and away more advanced than we are in planetary science at all. For Titan, we have exactly one heterogeneous reaction rate that has been measured. And so this is trying to figure out how these gases in the atmosphere are interacting with particles in terms of chemistry. And that's the citation. So there was a really amazing work that was led by Jonathan Fortney and a large group of people across exoplanets and planetary science that kind of just put together this huge laundry list of work that needs to be done to understand exoplanets. That work was published in 2016, and I know that very, very few things on this list have actually been done yet. I don't know what that says about a lot of different things. Maybe I can tell you my personal opinion later. But it's just to say that that list is is still kind of the most up-to-date version. There is a slightly shorter version of this work that was submitted to the Astro 2020 decadal as a white paper, but I think this is, and that one is also on the archive, but this is actually, I think, the more complete version. And so really this is just a plea for more laboratory work and also more theoretical work, because to really do justice to these amazing observations that are going to be done with James Webb and all the hard work that's gone into bringing these ground-based instruments and telescopes online, we really need to have our modeling tools in place. And to do that, we also need a lot of experimental work to be done. And with that, I think I have time for a couple of questions. Thank you.
Thanks, Sarah. That was both a great introduction and a highlight of several of the challenges. There is a mic in the room, but maybe to simplify it, and then Sarah, maybe you can repeat the question.
Yep.
Yes.
That flat line spectrum, that was from transmission.
Yes, that's a transmission spectrum.
Emission is a better way of looking for the atmosphere.
It's
If you do the Earth in transmission, you might get nothing. If you do it in emission, you get the spectral features of the atmosphere constituents.
I see George sitting there just like desperately wanting to answer this question. But yeah, so the question was basically, if you're trying to study an atmosphere, why are you looking in transmission? Emission might be a much better way to look at that. I think the easiest answer is that, we have to use the tools available to us and the geometries available to us in terms of exoplanets to be able to study them. And one of the easiest ways to study exoplanet atmospheres right now is from transmission spectra. But certainly people are thinking extremely creatively about all of the different ways in which we can use ground-based telescopes and also space-based telescopes, both the ones that exist now and the ones that are coming online in the future, to get any information we can possibly get from atmospheres. But again, we have to work with the data that we have at the moment.
Any other questions?
If not, I have one.
Go ahead, Kenan.
Oh,
Was there a second? Was there one back there?
Yeah,
Oh, yes.
good.
Sorry, you're right under the light.
So the question was, if aerosols dominate some of these atmospheres, would polarization help? Polarization measurements are certainly very useful for trying to understand particles in atmospheres. In fact, Titan's haze was discovered in polarization measurements from Pioneer. So even before Voyager, we knew that Titan was hazy from Pioneer polarization measurements. That's certainly something that the community has been discussing, but one of the other things that's important to remember is, at least with our space-based telescopes, those aren't, for the most part, with a few very important exceptions, actually exoplanet-only missions. And so there's a lot of trade-offs between all of the different communities in terms of the types of instruments that we're able to launch. And so I think that's been one of the challenges in terms of trying to get polarization measurements.
Yeah. So, Sarah, given I respect the wide parameter space and how much work we have to do, where should we start? What's the most important thing we should do first?
That depends on who you ask.
I'm asking you.
Yeah. Oh, geez, you really put me on the spot. I think that if our goal is a search for life, and I'm not saying that is the only goal or the most important goal, but if the goal is a search for life, I think we need to focus on the phase space that is closest to Earth at this point. Not because I think that is the phase space where most life would exist, but I think that's where we have the best chance of actually finding evidence for it at this point, only because that is the thing that we understand the best. And so in that sense, then I think trying to push, our temperature space a little bit wider, around 300 Kelvin. Our composition space, I think, is one of the more important things to try to expand in that temperature regime, because we really don't know a lot about how those atmospheres behave of other compositions. But honestly, I think, if people have a lab that's capable of doing any of these things, whatever is the easiest thing for them to do first, or to get funded first, or whatever, they should just do and do well and get it done and out there, because this stuff will get picked up by the community as soon as it exists, because there's so many desperate needs. Yeah.
Excellent. Thank you, Sarah.
Thank you.
And next up, we have George Ricker talking about review of Tessa's initial sky survey and future plans.
Okay. We've got the wrong, these things need to be switched somehow.
Oh, so you'll have to use this.
Yeah, use the screen.
No, but I mean, over there, you've got a problem.
Oh.
Yeah.
Oh, because you, so hit the,
I think you want to go to,
Yeah.
you don't want to be in page view or in a, there we go. Great.
Okay, thanks.
Well, that actually didn't fix it either.
oh, weird, okay.
I think you have to flip who's who on this because, yeah,
I'm not sure.
the preview.
It's on the right.
No, I think you have to, it's over in,
Yeah, go ahead, George.
well, I'm not 100% sure of this version of Keynote, but preferences, it's either preferences, slideshow, you want to be able to, mirroring, it's great.
Show pointer on the slide?
No, you're supposed to be able to mirror it.
Open display.
Open presenter display.
Yeah,
Click that off.
enable presenter display, there you go. Now go ahead and play.
Close the preferences. And just what?
It's thinking.
So, or he killed it completely.
Why is this always?
Well, we'll go to,
Yeah, I think
that's the
we'll-
one to do, just mirror it here completely.
Display.
That'll do it, it's under display, there you go. Showing, arrangement, yeah. There you go, mirror displays, that'll do it. Okay, now we're cooking. Great. All right, wonderful. So three PhDs are required to solve this problem. All non-specialists. Well, I'd like to share with you today some of the recent results that we've had from Tess. And it's been a 5-year effort since we were selected in 2013 with the mission. And I could say to Sarah that we're in the process already of making her job even harder by finding many more planets. But before this mission is over, we probably will find more than 10,000 planets. But they're going to be, as I'll point out later on, they're actually going to be a little bit easier to follow up than the ones that are in the set currently. Okay, I think this. Oh, this. Okay, cool. All right. So the basic science goals and drivers for Tess are described in this slide. The basic idea is that we're using the transit method, but we're really focusing on rocky planets and water worlds and habitable zone planets. And Tess is not trying to do anything other than find the best 1,000 or so small exoplanets as its primary goal. It turns out that it's also discovering a lot of other planets that are Jupiter-sized, Saturn-sized, and so forth. But the basic idea is that we're really focusing on making a large-scale survey of the solar neighborhood out to about 300 light years or so. This cartoon here actually shows the difference between what Tess does and what Kepler does. Basically, Kepler looked at 0.25% of the sky, and Tess is going to look at the other 99% plus. But it's going to do so in a way that it looks at the solar neighborhood in a fairly uniform fashion, and also it's focusing on objects that, or at least host stars, that are generally 30 to 100 times brighter than the ones that were detected by Kepler. And in order to do this, it has to have an enormous field of view, about 20 times greater than Kepler did, and it will cover about 6% of the sky at any given time. And to give you an idea of what this actually means, this image shows one of the 4 test cameras. So it's covering a 24-degree by 24-degree swath of the sky at any given time. The reason for the 4 quadrants here, those are CCDs, those are not individual cameras. The cameras are actually stacked atop each other. And for comparison, you could fit 10,000 moons, full moons, within the fields of view of Tess. And this is the Kepler field of view, which is enclosed within one of the 16 CCDs that Tess has. And then the LSST field of view is here, and this is the Zwicky transient factory. And basically, Tessa is taking 30-minute exposures of this enormous piece of sky and producing images. So in raw data, it's producing about 2 petabytes of data per year. And in addition, these full-frame images that it's taking are successive 30 minutes. And you can also look very easily in these for targets that you didn't actually intend or, in a premeditated way to look at. So there's something like 300 million stars and galaxies that you can actually examine. So it has a broad coverage temporally and solid angle that makes the mission work in the way that it does. So to give you an idea, another way to view this is the cameras themselves are described as cameras, but they really are photometers, and there's 64 million little light meters that are associated with it. And the precision is about 100 times better than what you can do on the ground. And the grasp, as I mentioned, is the 300 million stars and galaxies that we cover in a year. So basically, the fact that we're covering a large solid angle and we're doing it with exquisite precision is what makes the mission actually unique. So this is what the 4 cameras actually looked like. There's 3 here, and there's one over to one side when they were actually being mounted. And then this is the way the satellite actually looks. Now this is a bit of a misleading picture because it makes the satellite look a lot bigger than it actually is. It's only really about my height in total from both the spacecraft and the 4 cameras. And you can see the 4 cameras that are splayed out inside that cup at the very top. So the fairing for Tess, which was launched on a Falcon 9 in April of 2018, looks like this. You can see a human in the lower right-hand corner that gives you a bit of scale. And this is what the fairing actually looks like. And so you could put some pretty large objects in it. If you put Tess in it, it's this tiny little thing down in the bottom. So so if you actually compare this to the real image, this is that fairing with Tess actually undergoing integration. And then on April 18th, it was launched, and we spent 3 months doing commissioning. And then after that, the first science survey started. The mission has already accomplished the first year survey, which covered the entire southern hemisphere, and now we're about between a half and 3/4 of the way through the second year, which covers the northern hemisphere. So to give you the other thing that, in order to have Tess provide coverage in a continuous way, it was necessary to go into an unusual type of orbit. It's something called a lunar resonant high orbit, which has a period half that of the moon. So when the satellite actually runs, this animation shows the Earth at the center, and Tess is in orbit around it. It actually goes out further than the moon by a small amount. And then the moon, then you have this sort of a pattern that ensues. And if I stop the animation here when Tess is at apogee, you could see that this is a 3-body problem, and the moon is actually tugging on Tess. And then if I let and it's pulling it down in this image that is shown here, and if I let it run further, one of the things that'll happen is it'll go through a situation in which Tess, the moon is actually at the top. Tess will have gone through an entire orbit, and basically these perturbations cancel out. And as a result, this orbit is stable for at least a century with no fuel required. So it's sort of a magic solution that we came up with to make the system really work effectively. So this is the way the survey actually works. It's shown in this animation. The 4 cameras actually are splayed out, as I mentioned before, and we look at a large section of the sky at a given time, 6%. And then we step around with one of the cameras continuously looking at the south ecliptic pole for the first year, and then we flip the satellite around and then look at the northern hemisphere. And the reason that the continuous coverage at the ecliptic poles is so important is that's the continuous viewing zone for JWST. So any planets that we find in that portion of the sky can be observed at any time by Webb in a very efficient way. Otherwise, timing of observations to line up with the transits that would otherwise occur becomes a real challenge. So this really is for optimizing efficiency for Webb and other space-based telescopes to come, WFIRST and HabEx, LUVOIR, whatever. And this is the montage that we got from the first year survey. And if you want to imagine what this, where you would see this if you were on the Earth, if you were standing in the South Antarctic Peninsula, just a few 100 miles south of the tip of South America, this is what you would actually see. The object that's in the center of the field of view is the, and this is the sequence in which these little slices were taken. The object in the center is the Large Magellanic Cloud, and you can see that band going across the right-hand side from top to bottom in an arc. That's the plane of our galaxy. And if you blow this up, that's what the LMC looks like when it's when the image is enhanced. And then this is what you actually see in this corner, and then another point. So you can see there are a lot of stars that are being viewed at any given time, and so this is exactly what astronomers love to have. And this is the plane of the galaxy near the galactic center, and it's just a marvelous dynamic range within the instrument. So one of the things that we've done with Tess that has made many people in the community extremely happy is we've had an open data policy for Tess right at the beginning. There's no proprietary data associated with it at all, and so the job of the team is they're interested in doing science, but on the other hand, we're serving the community by making the data available as soon as we possibly can, and we've met all the requirements that were initially set to do this. And then in the first 4 days after we started the data releases, there were 3 million downloads and more than 60 terabytes of data were retrieved. And then currently, there's a very large amount of data that's continued, and I'll show you in a minute how the level at which this occurs. So Tess is now distributing about 10 times as much data from the archive at Space Telescope Institute at MAST as did the Kepler and is doing the Hubble mission. So it's turning out to be something that astronomers worldwide are very interested in helping with. As far as establishing the masses of the planets, you can't get that information from the transits alone. So we've established a follow-up observing program that involves more than 300 astronomers and a large number of institutions. And the map actually shows where the participants are located, and the little bars that show the photometry, imaging, and spectroscopy show the number of participants and the instruments that are being used. And so basically from this approach already, we've established 50 new planet masses. These are precision masses. A portion of this of this data has been published, but a lot of it is still in the process of being prepared for publication. So to get an idea of what some of the results actually are, that's what these are some recent papers on what we call the level 1 systems. These are planets that are smaller than Neptune, so they're less than 4 Earth radius, and they have to have masses or be able to establish masses from them. And you can see from the red characters in this left panel what the magnitudes are. Many of these are naked-eye objects, for example, or certainly naked-eye if you could see in the infrared. And the other thing is a lot of them are small stars, M dwarfs, which are, of course, the most common star in the galaxy. And then this is the list as it goes on. So as of December, as of yesterday, the number of planets that have masses published already in peer-reviewed journals is 37. And as I said, there's somewhere between 1.5 and 2 times that we know that are actually in preparation. So in addition, the community is still catching up on a lot of the planet candidates, and we've got 1,400 of those that are for which maths evaluations are in process. and we expect this number to be more than 2,000 by the end of the year. So to get an idea of what the publications are, this is the trending pattern on the AstroPH preprint server. We were expecting, based on what the community interest that we had when we were looking at early interest in 2018, that we'd be running about 140 per year, but it's turning out that there's already been 240 as of today. So the data is turning out to be useful for a large portion of the community. In addition to work that's being done on exoplanets, this is a tabulation that actually shows all the other types of astrophysics that people are actually being able to do. And the check marks mean that there are already results that have been obtained in the first year's sectors. And the other thing is that TESS is also detecting objects within our own solar system, which is something that we didn't actually anticipate how useful it would be in this regard. In fact, these images that are shown here, we've got an image of Sedna and KGU and then TG 422. So basically, TESS is able to, by stacking images successively, to get down to 23rd magnitude. And this is from a little lens that's about so big. But it just shows that in space, where there are not atmospheric problems or deviations, and you've got a stable instrument, things really just continue in terms of sensitivity according to the square root of the time that you observe. One thing that's actually going on, this is work that Matt Holman, Matt Payne, and Anders Paul are doing, is they've instituted a search for Planet 9, and it looks like, using the shift and stack method with the test data, that there may be a real possibility of helping narrow down the location and complete the identification. And then another thing that I'd just like to share with you for a minute is, this certainly has nothing to do with exoplanets or the solar system or whatever, but since TESS is able to go down to fainter than 20th magnitude, one of the things that it can do is look at extragalactic objects. And this is something that we found in January of this year. It was the first tidal disruption event by a supermassive black hole that TESS actually observed. In fact, it was the earliest tidal disruption event that had ever been observed. And this is an event where you've got a massive black hole, and then an unlucky star comes too close, and it basically gets shredded. Some of the hot gas goes out in a hyperbolic orbit or parabolic orbit, and some is actually trapped around the black hole where it emits it. And this is what the light curve from TESS looked like. We were lucky because this particular object was in the continuous viewing zone. In fact, we were looking at it right from the beginning of the sky survey in July of 2018. And as you can see from that lower trace, the colors indicate the different sectors that we were looking at it in. Nothing was going on. And then in January of this year, it just suddenly turned on. So and then when that actually happened, we had an explosion associated with it. This was actually the actual trigger for us to look at the event that we could see on January 21st came from an assassin network. And so this object is at a distance of about 100 megaparsecs and has a huge, it's 10 to the 12th times the luminosity of the sun. So, okay, so then the other question is, well, what's next for TESS in an extended mission? We received an A+ grade in the senior review that NASA just carried out for the astrophysics explorers, so we can actually look and make a plan for that. We're certainly going to be looking for longer period planets. We expect that we'll find planets that have durations up to a good fraction of a year. Many of the test planets are short period planets currently. There will be also, we'll be revisiting prime mission planets to make sure that the ephemerides are current and Webb can carry out the measurements that it needs to make. And then also there's a band, if any people who look carefully during that animation, you can see there was a little band around the ecliptic that we didn't observe, and we're going to go back and look at that more carefully. So the timelines for the coming decade for TESS and related missions are what are shown in this block going from 2019 to 2023. And if you project down from those dates, these are the other missions that are going to be operating in conjunction with TESS. There's a Swiss ESA mission called Cheops that will actually be able to help in some of the follow-up. Webb will launch. And then there's also greater possibilities that we'll be able to look for tidal, for neutron star and black hole neutron star coalescences in collaboration with LIGO, and then the LSST mission will occur. And this timeline goes out to 10 years, and we can see as the other giant ground-based facilities come on, we'll be able to operate in conjunction with them as well. So one other thing that we've been thinking about is sort of what could you do if you had another TESS or something that was comparable to TESS. And what this would do for you that TESS alone cannot do is this is an animation showing two TESS-like satellites, one of which is the original TESS, in orbit around the Earth, and that's the Moon. So this is like that animation that I showed you in the beginning. And then the other thing that you could actually do is you could flip the orbits, tip the orbits, so that you establish a baseline between these two of 93 Earth radii. And this would provide you the ability for using parallax to observe a large number of other objects and determine direct distances. So you can look certainly at main belt asteroids. That would be quite easy. In fact, we've already detected more than 100,000 asteroids, most of which have been previously known. Sedna is in that list, but also Planet 9, and we would have the ability to look at Planet 9 for a variety of assumed distances. And then the mission could also be used in a way where you could have the fields of view be overlapped, which would give you greater sensitivity, or you could stack them side by side and get more solid angle. And then certainly for one of these, if you had one more or two more or three more, it would scale accordingly. So we've been thinking about ways to the types of science that you could do, and something that really comes up in this is the possibility of looking for technosignatures. And there's a number of ways that they could operate together. And the other thing is that with the advent of what are called ESPA class frequent launch opportunities, these things should be a lot cheaper than was the case for TESS. And so I think this is really something that we're going to look carefully at. Yeah. So this is the takeaways from the TESS mission currently, and so I'd be happy to respond to any questions. Thank you.
There's one really short question. Very brief. Let's go. Can I go in the back because you asked last time? So yeah.
Given the follow-up resources that have signed up to now, how long do you expect, even with the haul of candidates that you have now, to be follow-up?
How long do we expect the follow-up to take?
How long is it going to take to have follow-up, like, for example, radial velocity measurements?
Well, the amount of follow-up that's been done so far is maybe 5% of what we can anticipate. The fact that TESS is in a long-lived orbit and the instruments are operating flawlessly, it means it could be more than a decade, because we're going to be finding additional, more interesting planets in the sense that they're going to be a longer period, and that increases the chance that we'll be probing more into the habitable zone. And so with the prospects of continuing the mission for another decade, I think that the astronomers are going to be busy for a long time.
Great. Thanks so much, George. We'll have some time for additional questions, hopefully at the end.
Okay, thank you.
Thanks. Watch your step. So the next talk is by Jacob Lustig-Jaeger and co-authors on the era of terrestrial exoplanet characterization. So we'll continue this great symbiosis between planetary science and astronomy astrophysics. Jacob.
Great, thank you. It's an honor to be here to talk about the era of terrestrial exoplanet characterization. Am I just hitting the arrow key?
It's right here.
Oh, great. And we just heard from George about how exciting this of a time it is. We're discovering Earth-sized planets that orbit other stars. And, but for now, we rely on the very talented NASA graphic artists to provide us with pictures of what these planets might look like. But the next big question we want to try to answer is, what is the nature of these planets, and how far along that path can we get? And so that's what I'm going to be talking about today. The first thing I'll talk about is what I mean by terrestrial exoplanet characterization, some of the goals, strategies, facilities, and targets that we'll be using to study the atmospheres of terrestrial exoplanets, and then some clues in our studies of terrestrial exoplanets from the solar system remote sensing community, particularly Venus and Earth, and some forecasts for the TRAPPIST-1 exoplanetary system. So as we begin, I like to think about 4 big picture questions that we want to answer for every single terrestrial exoplanet that we detect. The first is, does the planet have an atmosphere? We're biased towards detecting very short period, highly irradiated planets, and so many of them may have been eroded, and so they might not have atmospheres. But if they do, the next question we want to answer is, what's the nature of the planetary atmosphere? What molecules compose it? What's the temperature structure of the atmosphere? And for planets in the habitable zone, the next question might be, is the planet habitable? Is there evidence for liquid water at the surface of this planet? And for the very best targets, are there signs that the planet has a biosphere? Are there biosignature gases in the atmosphere or on the surface that could lead us to confidently conclude that we've detected life? So these are very big picture questions. And over the past few decades, the astronomy and exoplanet community has developed and applied a handful of different observing techniques that can be used to follow up and try to answer these questions. From photometry to spectroscopy and polarization at all different phases of a planet's orbit. But today I'm really just going to be focusing mostly on transits when the planet passes in front of the star. And I'll touch on phase curves, secondary eclipse, and direct imaging at the end. So we already have Hubble and Spitzer that have been operating for a long time and have begun to look at some of the optimistic terrestrial exoplanets that we've already discovered. And as long as James Webb launches on schedule now in 2021, we'll really take this to the next level and start to study terrestrial-sized exoplanet atmospheres in great detail. By the late 2020s, we'll have the 30-meter class ground-based telescopes to come online and help us out as well. And maybe sometime in the 2030s, we'll have a next-generation space-based flagship mission that could, again, take this an order of magnitude further and study Earth-like planets around Sun-like stars. But we already have detected numerous terrestrial exoplanets. So here we're looking at the detected exoplanets with known radii in the terrestrial regime between Mars size to 2 Earth radii across a few orders of magnitude and planet insolation. And I can put here a few boundaries here. The consensus in the community from population statistics is showing a boundary at about 1.6 Earth radii between gaseous and rocky exoplanets. So by terrestrial, maybe I'm talking about planets less than 1.6 Earth radii. And then I've also put the habitable zone down here, showing that we have already detected numerous habitable zone planets, but as we've heard from George, this plot is going to have significantly more targets in the coming years, thanks to Tess. Now, if we color these points by stellar effective temperature, a lot of these points are red, again reflecting our bias towards planets orbiting small stars. And further, if we make the size of these points proportional to how detectable their atmospheres will be with transmission spectroscopy, we can see that many of the points have all but disappeared as maybe Kepler detected them and they're too far away to be observable with follow-up. But some of these points have expanded and are good for follow-up. One of those that I'll start with is this planet LHS 3844b. This planet was the recent target of Spitzer observations by Laura Kreidberg and collaborators, where they were able to show that this planet is unlikely to have a thick atmosphere due to this large day-night temperature flux contrast observed in phase curve observations in the mid-infrared. And this planet also does not have a hotspot offset. So a thick atmosphere we would expect from 3D climate models to effectively transport heat to the night side of the planet, which would decrease the temperature contrast between the day and night side and likely offset the hotspot from the subsolar point or substellar point. So going back to our list of possible terrestrial targets, we also see that many of these planets are all in the same system. This is the TRAPPIST-1 system with 3 planets in the habitable zone, 3 planets interior to the habitable zone, and a 7th planet exterior to the habitable zone, a really exciting system. And so this will be a high priority target for James Webb. I've already mentioned the 7 known Earth-sized planets that transit a Jupiter-sized star. That's very cool. It's only 12 parsecs away, so even though this star is so faint, it can be observed. And we already know that these planets are unlikely to have low mean molecular weight atmospheres dominated by hydrogen and helium. So they either have no atmospheres or secondary outgassed atmospheres. So why are M-dwarfs the sort of best and only viable targets for follow-up with James Webb? This has to do with the size of spectral features from the atmosphere in transmission spectroscopy. Here we're seeing that around a TRAPPIST-sized star, that's Jupiter radius, this large CO2 feature at 4.3 microns exceeds 80 ppm, which is very observable with James Webb. But as we look at stars that are larger in radius, the size of these spectral features decreases dramatically, making it much harder to characterize these atmospheres. So for the rest of the talk, I'm going to come back to the TRAPPIST-1 system as sort of a bellwether for how much we can learn about terrestrial atmospheres in the near term with James Webb. So we'll start with Venus as an exoplanet, sort of as a probe of how we might detect and start to constrain the composition of terrestrial atmospheres. So in 1761, a Russian astronomer, Mikhail Lomonosov, detected the atmosphere of Venus by the refraction of stellar light through the thick Venus atmosphere as it transited the sun. As you can see on the left of Venus's disk in this very beautiful image, the small amount of light that's been enhanced a little bit, but you can still see it. That's essentially what he drew in his notes here and concluded that Venus must have an atmosphere. So it was relatively easy to detect Venus's atmosphere. But characterizing Venus's atmosphere, understanding the greenhouse-heated lower atmosphere has been incredibly difficult due to the thick sulfuric acid clouds and hazes which blanket Venus. So this should scare us. We've already seen this plot from Laura Kreidberg's GJ1214b paper showing this incredibly flat transmission spectrum with no spectral features discernible due to likely this high altitude cloud or haze. So how can we take these lessons learned with us into studying the TRAPPIST system with James Webb? We conducted some self-consistent 1D photochemical and climate models of Venus-like planets for all of the TRAPPIST-1 systems to figure out how much observing time James Webb would need to detect these atmospheres using the same technique, transmission spectroscopy, that was used for the super-Earth GJ1214b. So here we just want to see the spectral features likely due to CO2. And so if this planet doesn't have a sulfuric acid cloud, then the atmosphere could be detected in just 4 transits with James Webb. This is TRAPPIST-1c. But if we add a self-consistent sulfuric acid cloud deck, then this decreases the amplitude of the CO2 features relative to the continuum and flattens the spectrum substantially, such that it would require close to 20 transits to detect this atmosphere with the same precision. So it's not impossible to detect the atmosphere, just much more difficult. Now, a really interesting effect can be seen as a function of semi-major axis if all of the TRAPPIST-1 planets are Venus-like. So we've already looked at C, and the story for D and E are relatively similar, with the amount of transits needed to detect a cloudy Venus-like TRAPPIST-1e would be up to 30 transits. But as we go to the cooler planets, E, F, and G, the sulfuric acid clouds form lower in the atmosphere, such that the cloudy, cold Venus atmosphere is no more difficult to detect than the clear atmosphere. So this begs the question, how deep into the atmospheres of these planets are we even probing with transmission spectroscopy? So here we're looking at the maximum pressure probed in the transmission spectrum for these clear and cloudy Venus-like models compared to the surface pressure of Mars, Earth, and Venus. And we can see that we're probing the Mars and Earth pressure regime, but all of these models have Venus surface pressure. So we're at least 2 orders of magnitude in pressure away from the surface of these planets using transmission spectroscopy. So these trends diverge for the close-in planets due to the physics that controls the continuum of these spectra. So for the clear atmospheres, refraction limits the depth you can probe into the atmosphere, which has a geometric effect as a function of semi-major axis that scales with the size of the star as seen from the planet. Whereas clouds form at different altitudes or different pressures in the planet's atmosphere due to the temperature at which that cloud formation would occur. But particularly interesting and perhaps tricky situation is this trend seen sort of as we approach the temperate regime, where these planets, if they're thick, cloudy atmospheres, look similar to thin, tenuous atmospheres like Mars that may be sculpted by atmospheric escape. So atmospheric escape modeling of the TRAPPIST-1 planets suggests all of the planets, except for H, could have lost substantial portions of their atmospheres. So are we seeing thick and cloudy atmospheres or thin, tenuous atmospheres? This will be a question that may be difficult to answer with James Webb. So one of the benefits of the exoplanetary population is the size, the amount of statistics we can work with compared to solar system studies, but we have to be cautious about degenerate physical mechanisms that can produce similar trends in populations. So now we'll switch gears a little and we'll talk about Earth as an exoplanet as we can guide our studies of habitability and our search for biosignatures. So I'll begin here with a recent paper that shows Earth's empirical transmission spectrum calculated using almost a decade of solar occultation data as this spacecraft orbited the Earth. And here we can see tons of molecular features giving us an indication of what's possible with high signal and noise, high spectral resolution transmission spectroscopy. We can see large CO2 features and biogenic ozone features, methane features, water features, N2O, HNO3, lots of atmospheric chemistry that can be probed in the transmission spectrum. And to really appreciate this, I've done a few levels of zoom here. If we zoom into the 4.3 micron CO2 feature, we can see the forest of lines that make this band up. A further zoom in really shows the structure of these lines, and one more level really just shows that this spectrum has no noise. And if you're an exoplanet scientist, this may be the highest signal to noise, highest spectral resolution spectrum you've seen, and it blew my mind, which is why I had to make this plot. But if you're a solar system scientist, I probably look like a doofus because you're used to stuff this high signal to noise. But this type of solar system or Earth remote sensing observation that can be recast and thought about in terms of sort of what we can do with exoplanets really gives us an opportunity to validate our models and sort of temper our expectations for what's possible. If there's things in the spectrum we can't learn about Earth, then we'll never be able to learn those for exoplanets, such as the water features in the spectrum are really small. We'll come back to that. So now how do we take this and think about observing the TRAPPIST-1 system with James Webb? First, I'll talk about modern Earth-like planets, supposing if the innermost TRAPPIST-1 habitable zone planet, TRAPPIST-1e, has an atmosphere similar to the modern Earth. So here we're looking at transmission spectrum of this Earth-like planet run to photochemical equilibrium with the spectral energy distribution of the star, which allows methane to build up to larger abundance than we see for the modern Earth, given the same surface fluxes of methane. And so this spectrum has gigantic methane features and CO2 features, as well as you can see oxygen and ozone and O2 in sort of the visible and near IR. If we add clouds to this model, it doesn't change the picture substantially. These are water clouds. It obscures water, but it doesn't affect the strength and detectability of the methane and carbon dioxide features. And if we apply James Webb noise calculations applicable for 50 transits, a significant time investment, just for sort of a reference to where the signal to noise is in this spectrum, given a substantial observing amount of time, we can see that methane and CO2 are detected at strong significance here. They can be detected at 3 sigma in just 2 or 3 transits, but water, like we saw in the empirical transmission spectrum, is incredibly difficult to detect as it's concentrated in the lower atmosphere, where the transmission spectrum just doesn't probe. Zooming in between 1 and 2 microns, we can see that these oxygen features are incredibly small. It would require well over 100 transits to detect at just 3 sigma, so not something we should expect to be doing. However, these oxygen features could be gigantic due to collisionally induced absorption if this planet lost a substantial amount of oceans early on and built up a 10-bar desiccated oxygen atmosphere. So this is a testable hypothesis with the James Webb Space Telescope, because these oxygen features could be detected in the order of 25 transits. Now, going back to our Earth-like atmosphere case, looking at the mid-infrared, we can see the ozone feature at 9.6 microns is swamped by noise, even for 50 transits, indicating that, evidence of oxygenic photosynthesis in the TRAPPIST-1 system and in terrestrial exoplanets observed with James Webb would be sort of beyond what we expect to be able to do. And this is in agreement with other recent works that have been published this year that sort of also agree with this picture of a difficult time detecting oxygenic photosynthesis as biosignatures. Now, we could also use the geologic record of Earth to look back at what the atmosphere might have been like during the Archean, when methanogens would have pumped out lots of methane and before the rise of oxygen. So here we're looking at the TRAPPIST-1e with one of these atmospheres, which doesn't have oxygen, but once again, the picture isn't too different. We see large methane and CO2 features, tiny water features that are difficult to detect. Again, clouds really just obscure water, but they don't obscure the methane and CO2 much. Again, just a handful of transits would be needed to detect those CO2 and methane features, but water would be more difficult. A haze could form on these planets, which would obscure these molecular features, make it more difficult to characterize the atmosphere. In some circumstances, that haze could be a biosignature in and of itself, but only if sufficient context is provided in the retrieval of CO2 and methane abundances to conclude that it would only form from photochemistry involving those biogenic gases. So to conclude this little section, I would say that tropospheric water will be really difficult to detect in the atmosphere of planets transiting the TRAPPIST-1 system, but a next-generation telescope really should be designed such that it can probe habitability and try to provide context for what biosignatures we may be able to detect. Looks like I'm out of time, so I'll put up my conclusions and take any questions. Thank you.
Time for one short question, if there's one. Yes.
For the present day simulations of Earth, how different would it be if you were to run that through your 3D atmosphere, where it has things like heterogeneous chemistry, ozone loss, those sort of things? Would you still see the same picture, or would it be different?
Yeah, that's a fantastic question for those who didn't hear it, about what the estimates for the modern Earth would be like using full 3D calculations, including chemistry. It would certainly be interesting. Work by Howard Chen has shown some abundance variations as a function of longitude on planets, but those variations seem small for something like ozone compared to the sort of sensitivity we would have from a retrieval. So I think maybe the clouds could be lofted higher and make this picture of detecting methane and CO2 a little bit more difficult given higher altitude water clouds. But I think in general, the picture of methane and CO2 perhaps being detectable and water being more difficult would hold. But yeah, we'll see.
Thanks, Jacob. And next up, we have Stephen Kane talking about Venus as a laboratory for exoplanet science.
Thank you. Thank you, everyone, for coming along. And thank you to the organizers for inviting me, and especially for putting me at this stage in the series of talks. Because what we've heard so far is a story arc about what kind of laboratory experiments we need, the detection of exoplanets and characterization of exoplanets. And I'm going to be talking to you about the case study of Venus, which Jake just spoke briefly about. So this background image is, of course, one of these beautiful artist images that Jake mentioned earlier in his talk, where we are trying to get to a point of characterization which is utilizing the atmosphere of the planet. This is how we're going to be able to hopefully infer surface conditions. However, one of the things to remember is that when you're talking to an exoplanet astronomer like me, and I mention this to my planetary science colleagues all the time, is that you are in essence talking to a stellar astronomer. What exoplanet people do is that they observe stars very carefully and they infer the presence of an object orbiting it. That is the extent of the planetary science knowledge of, for the most part, for the exoplanet community. So, in order to progress further, we need to gather around this atmospheric data and really bring to bear all of the knowledge that exists within the various communities that can actually speak to how the surface processes are influencing the atmosphere. And this is a key point, because it means that since this is a remote science, for the most part, planets that we can't even see, then we're going to need to be very careful about how we do this, and we're going to need to do it based on planetary science model where we actually do have data. Now, this became most apparent to me as an exoplanet person about 10 years ago, because 10 years ago was the launch of the Kepler mission. And the Kepler mission was a mission which was designed specifically to probe deep into the terrestrial realm where exoplanets had not significantly trespassed upon before. And towards the end of the mission, we started to see diagrams like this one, where we have this huge inventory of exoplanets. We are successfully pushing down into the terrestrial regime. But you'll notice there that we have our 4 units of measurement. Jupiter and Earth represent order of magnitude difference. Neptune is nicely in between. But the thing to always remember when you're looking at a diagram like this is if I just make a very subtle change, like this, don't know if you could see what the change that happened, but the label on the y-axis changed. I changed the picture on the Earth, and it's exactly the same diagram, but of course with very, very different implications about what it is that we're discovering, because when you look at those data, you can see that the orbital period shown on the horizontal axis is, for the most part, not Earth-like. What we're doing is we're discovering potential Venus analogs. That's what Kepler and the transit method as a whole is most sensitive to. And so it's something to keep in mind. And so when I was analyzing the data from Kepler and thinking about this more, and I realized that even though Kepler was designed to try and statistically determine the occurrence rate of Earth-sized planets within the habitable zone, what it's actually better at doing is it's better at determining the occurrence rates of Earth-sized planets closer in, where we're more sensitive. And this is something that myself and my colleagues refer to as the Venus zone. And the Venus zone is the companion to the habitable zone, which is essentially interior to the inner boundary of the habitable zone, which is where an Earth analog would be pushed into a runaway greenhouse state. And from doing this study, from the statistics of the Kepler discoveries, we found that for most solar-type stars, then we're looking at an occurrence rate of about 50%. So around 50% of solar-type stars are expected to have a terrestrial planet meaning smaller than about 1.5 Earth radii in this zone. So this means that there's a lot of these planets out there, which makes it even more important. Now, what I want to do for the remainder of the talk is tell you about why this is so critical to understand Venus as an exoplanet, given what I've just told you. Here is a beautiful picture of Venus. This is a picture of Venus which was taken by the Japanese spacecraft, Akatsuki, which is currently orbiting Venus, has been for almost 10 years. And it's been returning amazing images like this of Venus and the clouds at various wavelengths, particularly in ultraviolet. And one thing that we certainly do take for granted now at this particular epoch is that we know that despite what we see at the cloud tops, that the surface looks more like this. And that the surface pressure is around about 92 bars, and surface temperature is about 450 degrees Celsius, and all of the terrible hellscape things that we often describe it with. However, the point I wanted to make in talking about this is that you don't need to go very far back in history when people did not take this for granted. And in fact, if you go back only a few decades, you'll find a whole range of science fiction and film that depicted the surface of Venus as this very temperate, perhaps jungle-like environment. So in 1959, the Three Stooges went to Venus, and it was about as bizarre and weird as you would expect a Three Stooges film visiting Venus to be. I won't say more than that, but you should watch it. The one on the right was the last film that was made about going to the surface of Venus. That was in 1965, and in that case, American astronauts discovered that the dinosaurs actually escaped the KT event and went to Venus. Who knew? So what is the point here? Why did we stop making these films? As I said, 1965 was the last one. Because Mariner, the combination of data from the Mariner and Venera programs revealed that the surface of Venus was far different from what we expect and what had been, for the most part, hidden by the thick clouds of the Venetian atmosphere. So, would we have figured this out otherwise? Well, maybe, but the issue of having to go to the surface to Venus to understand the full extent of how wrong we were has been something which has been explored quite a bit in recent years with the use of climate models, which are usually Earth-based. And one of my colleagues, Francois Forget, who's been doing a lot of work on this, and he has used climate models to investigate the surface of Earth and Venus and Mars and even Pluto, and he was part of the New Horizons team that investigated when you might expect the collapse of the Plutonian atmosphere as it moved away, further away from the sun. Here's what Francois had to say about Venus. He said, if Venus did not exist in our solar system, we would not dare to imagine it. And if you do conduct that thought experiment, if we did not have Venus, if we just had Mercury, Earth, Mars, and so on, then you might imagine models where we try and move Earth closer to the sun, what would happen to the Earth atmosphere, and the current models are unable to transition from a temperate to a full post-runaway greenhouse that we now see Venus in. We might predict that it'll get a little bit hotter, but as Francois said, we would not predict the current conditions on Venus. We would be spectacularly wrong. So what can we do at the moment? Well, as I said, most of our models are Earth-based, and it means that they're constrained to a lot of the physics that is inherent in those kinds of codes. And we have been using this to try and make predictions for exoplanets which are in the Venus zone. There was one in particular that for a couple of years ago was one of the Kepler discoveries, Kepler 1649. And this was an interesting one because it's a planet which is only slightly larger than the Earth and Venus, and it receives about the same insolation flux, which is about 1.9 solar constant. What we did was we used a climate model called Rocky 3D, And based on various scenarios, we tried to push this to the limit, this model to the limit. And in general, what we find, which is what a lot of other models find, is that when you start from temperate surface conditions, that once you get above about 10 bars, the atmospheric chemistry changes sufficiently that your model can no longer reach radiative equilibrium. And so that's what we will find in this case. By the way, in this case, what you're seeing is a temperature map of the final stable state of the model. And we are using the Venetian topography. We tried a variety of topographies. The model is sensitive to that. But in all cases, what we did find is that for this particular planet, all scenarios quickly started to escalate the temperature. It started to push them into what we refer to as a moist greenhouse state. But we were not able to go any further than that. So the topography of the surface can have other influences on the atmosphere that we don't necessarily have observed recently, and we certainly will not observe for exoplanets. Going back to data from the Kepler mission, this is an image from a couple of years ago, and this is an extraordinary image showing patterns in the clouds of Venus. What you are seeing is a gravity wave, a standing wave, which is being produced in the Venetian atmosphere, and it's being produced by interaction with the Venus topography. If I go back to the previous image for a moment, you can see in the middle on the right is the continent of Aphrodite Terra. Now, what happens when a 90-bar atmosphere encounters a continent at the surface? And keep in mind that when you're more than 90 bars, that's equivalent to a kilometer depth in the ocean. That's way below the safe scuba diving depth. And that interaction can be profound. And it's having an effect on the circulation of the atmosphere that we are not incorporating into our models. And so this is something else that we need to try and be more careful about including. So there are many, many outstanding questions about Venus. So for example, I have a couple of examples here. If you want to see the full list, then myself and Jim Head and others in the room, many of my collaborators published in JGR Planets a summary of these, but here's just a couple. We don't know much at all about the interior structure. We assume that Earth and Venus formed under similar conditions. That may be a fair assumption, but we don't even know to a very good precision the moment of inertia of Venus. Has very slow rotation, doesn't have a moon. We have very little knowledge of the gravity field. And so we don't even know really the size of the Venetian core to good precision. And that's a problem. This is obviously related to the tectonic history. What we're really trying to understand is the volatile recycling, resurfacing, subduction. Is there current subduction? The best resolution maps we have of the surface are from Magellan data. And as Mikhail likes to say, that if we had the same resolution data of the Earth, we wouldn't detect the Grand Canyon. So we're missing a lot of information about the surface of Venus and about ongoing subduction at the surface and if it truly is a stagnant lid. The atmosphere is critically important for our models. We only have the Venera data all the way down to the surface, and we desperately need precision temperature, pressure, composition data all the way down to the surface. And finally, and perhaps most importantly in terms of habitability, was Venus once habitable? Was there surface liquid water? If we do indeed assume that they formed under similar conditions, there is growing empirical data to indicate that the surface of Venus did once look like this. And this is extremely important for habitability because one of the mistakes we often make, and we should try and avoid this wherever possible, is that we study the solar system at the present epoch. But to only study solar system objects at the present time, you're missing vast amounts of information. And the evolution of these planets, particularly if at 2 gigayears, if we had observed our solar system as an alien civilization and come to the conclusion that there were 2 habitable planets in the system, then that's obviously something that's extremely important for informing our target selection for exoplanets. As Sarah said earlier about how the habitable zone is used, we don't know if those planets are habitable, but we are using Venus as a demarcation for the inner edge. And if they did once have liquid water, then that's something important. So, Let me conclude with 4 main points. Firstly, as I said, terrestrial planets are extremely common. We know this now, and the transit missions, such as Kepler and now Tessa, are giving us many, many more. And as I said, the great news for doing a statistical study of the possible occurrence of Venus-like planets is it's great times for that. I sometimes refer to Tessa as the mean, lean Venus-finding machine, and I hope that George takes that as the compliment it is certainly intended to be. So, but there are many of the targets which are going to go to JWST are going to be exactly the kinds of targets that Jake was talking about, where we're possibly going to need to try and understand these flat spectra or look for these transparent windows in the atmosphere where we can infer what's going on at the surface. Secondly, habitability. We often hear the phrase that we only have 1 data point when it comes to habitability. We should all be upset, of course, when we hear that, because if we're, insofar as we're talking about Earth-sized planets, we have at least 2. And demarcating the boundaries of habitability, regardless of whether Venus once had surface liquid water or not, is just as important as knowing where life is right now. As I said, there's this time axis that we always need to keep in mind. Thirdly, like I said, there's an interesting history to the exploration of Venus. If you're really interested in that, you should talk to Jim Head about that, because he knows a lot about that history. But in particular, our view of what the surface was like changed dramatically not so long ago. And we had to go there to do it. And fourthly, Proxima Centauri b is by definition the nearest exoplanet, and we are not sending a lander there. I'm sorry to say. We are not going there. We're not going to get surface in situ data of Proxima Centauri b. So what does this mean? Well, those last 2 combined, the fact that we're not going to get in situ data for planets that we can't even see, and that for the nearest Earth-sized planet, we had to go there to understand. Those 2 points combined should scare the hell out of everybody like me and Jake who are interested in inferring the surface conditions of exoplanets. Because the way I see it is that Venus is a real test for the exoplanet community. If we, insofar as we struggle to understand the surface of the nearest Earth-sized planet, one that we can easily resolve from the ground, then that is going to directly impact our ability to infer anything about the surface conditions of planets that we can't see, we will not visit, and are many parsecs away. So, on that happy note, I'll leave there for any questions.
So we have time for a few questions. Yeah.
Didn't Carl Sagan infer the Venus had a really high temperature from the radio measurement?
Yes, that's true. It wasn't just Mariner and Venera. There were starting to be indications. Of radar measurements. But once again, that's something that we just won't get for an exoplanet.
Any more questions? All right. Thank you, Stephen. Next up, we have Melody Cow talking about planetary magnetism and exo-Irori. We had trouble with it before.
Don't worry about it. Okay, no worries.
You'll get a yellow light at 2 minutes left.
Okay.
Just right there.
Okay, perfect.
Go ahead.
Good afternoon, everyone. It's so great to be here at my first AGU. And I'm really happy to be closing this set of talks because as we have been discussing quite a fair amount today, this is Venus's atmosphere. So as a radio astronomer and as someone who studies magnetic fields on planets, I actually spend a lot of time thinking about planetary atmospheres. This atmosphere of Venus, you can see that thin sliver of brightness that Jacob pointed out. It's that very delicate atmosphere. And the reason why I spend so much time thinking about planetary atmospheres is because since their birth, all planets in a stellar system have been interacting with their sun's space weather. So this is an image of the sun's corona taken during the 2017 total lunar eclipse. And what you can see, if you can see that loop on the right-hand side of the moon, that is what's known as a solar prominence, or dense plasma flowing along tangled and twisting magnetic field lines. And sometimes when those field lines reconnect, they actually can eject a lot of hot ionized plasma magnetic field lines that impinge on a planet's magnetosphere and actually carries away atmospheric mass. And so this is measurements taken with MAVEN of Mars's atmospheric loss response during a solar storm. And you can see here that during the solar storm, Mars loses its atmosphere by approximately 100 times increased rate as opposed to when there's not a solar storm. So we think that Mars's magnetic field may have played a role in this strong atmospheric loss response. Over about 4.5 billion years, Mars has lost nearly most of its atmosphere, but early in its lifetime, the engine that was generating its magnetic field shut down and left a weak remnant field frozen into its crust. As you can see here from work by David Brain and Fran Bagenal at CU Boulder. So we know that when Mars's magnetic field rotates into view of the sun, that it actually loses less atmosphere than when its magnetic field is rotated away from the sun. So in contrast, Earth's magnetic field is very different from Mars's magnetic field. Most of the energy in its magnetic field is contained in its dipole component. Mars has essentially no dipole magnetic field. And we can see here that during the same solar storm, Earth actually loses its atmosphere at a rate that's about 10 times less than Mars's relative response. So what I want you to be noticing here is the difference between the gray and the red, just the distance between them for Earth versus Mars. So magnetic fields are generated in the interiors of planets, essentially by conducting fluids and their motions, as well as the Lorentz force, we end up with magnetic induction that drives and sustains these fields that we see. And so this means that interior properties like conductivity, viscosity, and density stratification, for instance, can actually influence what we can observe, like magnetic field strengths, their topology, or even time-changing behavior. And so this means that by studying magnetic fields on planets, we actually also can probe their interior properties and dynamics. And so this is a recent example of Jupiter's non-dipole magnetic field component that was mapped using magnetometer data from Juno. And what I want you to take away from here is that the northern hemisphere of Jupiter has actually a strongly non-dipolar field. And the southern hemisphere is predominantly dipolar, which is why you don't see much in this particular map. And so this lopsided magnetic map of Jupiter was actually quite surprising. Prior to these measurements, most Dynamo simulations of Jupiter had predicted a predominantly dipolar field. And what this particular result suggested is that perhaps Jupiter might have a stratified dynamo region. Maybe its core is not actually a solid core, but it's essentially dissolving into the metallic hydrogen region of Jupiter. And this just gives you a taste of what, if we could do something like this for planets outside of our solar system, the interesting stuff that we could learn. So unfortunately, we're quite a while away from getting that quality of data for objects outside of our solar system. So what instead astronomers do is we aim to measure magnetic fields and essentially both test dynamo models and also measure empirical scaling relationships between their magnetic field properties and observable properties like flux, temperature, mass, rotation rate. And so this is an example where Uli Christensen in 2009 took planetary dynamo simulations and scaled them up to stellar parameters. And the main result of this particular work was that he found that the convected energy flux in the interiors of these objects seemed to be the primary component to studying the magnetic field strengths of planets all the way on up through low-mass stars. So by measuring magnetic fields on planets outside of our solar system, we can test models like that. And these are some examples of methods that we can actually look forward to in the next 10 to 20 years of actually measuring planetary magnetic fields. So Antonia Oklopcic, who is currently at Harvard and will be moving to Europe later next year, she is leading the theoretical development of actually measuring the spectropolarimetric response of absorption from the helium-1083 line. Emission of the helium-1083 line in hot Jupiter systems. This is very new work. She just submitted it in October, and there's a team on Spiru that's going to be looking at whether or not this is feasible to actually measure using modern-day instruments. We can also directly measure magnetic field strengths by actually detecting the radio aurora of exoplanets. And you can see here what became known as the first detection of the radio aurora from Jupiter by Burke and Franklin in 1955. So far, there have been a lot of teams that have been working towards making these measurements for well over 30 years. I expect that we'll be starting to see some exciting results from low-frequency radio arrays like LOFAR or SKA. And I encourage you guys to check out the newest results from a LOFAR survey by Harish Vedantam, Joe Callingham, and then Jake Turner. So for indirect methods, there's interest in inferring magnetic fields from atmospheric bow shocks. This still requires a lot of modeling, and these signals are quite difficult to disentangle from other physical processes. And then we also can infer magnetic field strengths from what's known as star-planet interaction signals, where essentially you have a planet that's close into its star and it's interacting with its star's magnetosphere. And it creates this orbitally modulated emission, So using the star-planet interaction measurements, Wilson Colley at CU Boulder actually earlier this year showed that the magnetic fields that he inferred, which were quite strong, around 100 Gauss for hot Jupiters, and to put that in perspective, Jupiter's dipole field is around 10 Gauss. So these strong magnetic fields that he inferred could actually be explained if he took all this excess thermal energy from the planet's close-in stars and dumped that deep into these planet interiors. So if he assumed that there was 100% efficiency conversion of this extra heat from the host stars, then he could explain these very strong fields. And then finally, the method that I actually favor is using brown dwarfs to study planetary dynamo mechanisms. And this works because brown dwarfs and gas giant planets have convective dynamo regions. And so the same physics is occurring in both kinds of objects, and this means that brown dwarfs can actually act as probes of gas giant dynamos. And we do this by using the two-component of brown dwarf radio emission. So you'll notice here that there are these pulsed peaks in the radio emission. This is the signature of radio aurora for brown dwarfs. And then as well, there's a low-level, slowly varying quiescent component. So as is the case for planetary aurora, if we detect radio aurora on brown dwarfs, this is a direct measurement of brown dwarf magnetic fields. And it turns out that when we look at Wilson's hot Jupiter measurements within the context of cold and isolated brown dwarfs, something really interesting shows up. And it's that these cold brown dwarfs, which don't have a source of extra thermal energy from a host star, actually also have anomalously strong fields. And I think the fact that right now the fields that he's measuring rely on this 100% efficient conversion, and we know that nature tends to not be 100% perfect. It seems that when we look at these anomalously strong fields as a group, that there's something extra going on in these interiors. So additionally, we also actually know from brown dwarfs that planetary mass objects can generate extraordinarily strong magnetic fields. This green object here is the first planetary mass object that has had its magnetic field directly measured using radio aurora. It has a mass of roughly 12.5 Jupiter masses. It's quite young. And it's a proof of concept that, that brown dwarfs and planetary mass objects in particular can actually generate the aurora that we need to measure magnetic fields at planetary masses. And in addition, that cold planetary mass objects without an extra thermal source can also generate magnetic fields that are 2 orders of magnitude stronger than what we expect them to be. So one of the things to keep in mind about that particular planetary mass object is that brown dwarfs, as they age, they cool along the spectral sequence, similar to how as planets age, they cool. And so one of the questions that has come up is whether or not this particular object is perhaps has such a strong magnetic field because it is so young and hotter than typical planetary mass objects. And so we can actually turn to the quiescent emission from brown dwarfs to get a handle on this question of how magnetic fields evolve as planets age. And so this is a composite image of Jupiter's radio emission. There are 3 main sources of radio emission from Jupiter. We see this beautiful image of thermal emission from Jupiter's clouds, as well as the synchrotron radiation from its radiation belts. And then this is the UV aurora from Jupiter, as just for illustration's sake. So for brown dwarfs, their thermal emission will be too faint to see. And this means that all of their remaining radio emission is going to come from, is going to indicate that there's a magnetic process happening there. You're going to need to have magnetic fields and electrons to accelerate around those magnetic fields. But what this also tells us is that we're going to have to look at populations of brown dwarfs. And this is because if you look at a single object and it doesn't have radio emission, that doesn't really tell you, that can't distinguish between whether or not it's missing its magnetic field or if it's missing its electron source. And so there are efforts now to begin building up population statistics of brown dwarf radio emission, such as this survey that I'm just completing right now of young brown dwarfs. And we're actually starting to see that young hot objects do not actually have a significantly different radio occurrence rate compared to old and cold objects. And so for those of you who are studying planetary atmospheres, one of the questions that you may want to be considering is, given these results that we're seeing of strong magnetic fields sort of living throughout the lifetime of these objects, what kinds of implications does that have for their atmospheres? So in the last few minutes, I want to touch on what we'll be able to look forward to in the next decade. I encourage you to all check out the white paper that I co-led with J. Sebastian Pineda at CU Boulder. For the first, one of the things that I've really been thinking about is what are magnetic topologies? And this is because this particular Dynamo model that I showed you, it actually has a subtlety, and it's that the magnetic fields of these objects that are being modeled are assumed to be predominantly dipolar. And so this begs the question, what if there are objects out there, like these ones that disagree with this model, that do not have dipole-dominated magnetic fields? And radio emission, one of its current limitations is that we don't actually get much topological information from it. And it's because the radio emission is emitted at the local magnetic field strength. So closer into the planet, it's going to be emitted at a higher frequency where the field is stronger. Further away from the planet, it'll be emitted at a lower frequency where the field is weaker. And moreover, we don't actually know that aurora trace dipole fields. It's an assumption that was made commonly when brown dwarf aurora were first discovered. But this is an actual video of Mars's UV whole planet aurora. And I'll remind you that Mars does not have a dipole field. So what I would love to see from the planetary community is actually radio measurements of Mars, because I've been trying to find that information and I cannot find it anywhere. So with current instruments, we've actually starting to see that, that it is quite possible to use radio emission to back out the topologies of these objects. So using the Very Long Baseline Array, Arnold Benz in 1998 actually resolved the magnetosphere of an M5.5 dwarf, a UV study B, shortly after a flare. And what you can see here is what is interpreted as the flare that has been confined in its large-scale dipole field. And then with the upgraded Very Long Baseline Array, Jackie Villadsen is starting to get a handle on the magnetic polarity of that particular object. So if we invest in next-generation radio observatories that include both the sensitivity and also the long baselines that we need, we can actually conduct similar observations of brown dwarfs and potentially one day exoplanets outside of our solar system. So another question that I'm very interested in is what are the characteristics of exo-Irori? So I showed earlier in 2016 that some Jovian auroral tracers also seem to trace brown dwarf Irori. And in particular, we were looking at, we noticed that radio aurorae seem to be traced by infrared variability, as we'd expect, since Jupiter has quite a strong infrared aurora. And what I want you to take away here is that recently my student is wrapping up a project in which she's showing that while low amplitude 1.2 micron variability seems to not trace aurora, high amplitude 1.2 micron variability, which is this green hump, seems to show very tentative and personally for me extraordinarily exciting hints that maybe the 1.2 micron emission that traditionally has been associated with clouds on these objects can actually also have a component that's excited by magnetic heating in their atmospheres. And so with the next generation of facilities like JWST, LUVOIR, or the ELTs in combination with our radio facilities, we'll be able to conduct multi-wavelength observations to constrain the spectral response of aurorae outside of our solar system. And so finally, the last question that I'm very interested in is, do brown dwarf satellites power aurorae? And most astronomers, when I tell them about aurora, they imagine a solar wind interaction. But in brown dwarfs, they don't have a solar wind. Instead, we can turn to examples in our own solar system where satellite interactions actually are important for aurorae inside of our solar system. And so, for instance, Io populates a torus of plasma around Jupiter that interacts with Jupiter's large-scale magnetosphere, and that actually excites the main auroral oval on Jupiter. And then similarly, as Io is traveling through Jupiter's magnetosphere, it excites what you can see, these streaks and dots of these Io Jupiter footprints. So I'm running out of time, but the main thing that I want to emphasize is that there are teams that are now trying to look for Io Jupiter analog auroral interactions. And if we can find that, this is an example of TRAPPIST-1, where no radio emission was found. But if we can find examples where there are Io Jupiter analogs occurring outside of our solar system, that would actually be a direct probe of the magnetism and ionospheres of potentially exoplanets around these brown dwarfs. And so by using brown dwarfs, we're not only getting a handle on gas giant magnetism, we're also beginning to be able to probe terrestrial planet magnetism. And I will just leave it at that. Please vote for your friendly neighborhood radio array. For those of you who are on decadal surveys, the radio astronomy community really is the key to this next era of exoplanet magnetism.
So we have time for one quick question. Yeah. All of it.
Do you have a preferred wavelength range in radio observation?
Well, funny you ask. Yeah, so brown dwarfs, we're going to have to go between roughly 1 to hundreds of gigahertz. And then gas giant planets, just based on their predicted magnetic field strengths, will have to be in the hundreds of megahertz. And then terrestrial planets will actually have to go above the ionosphere into space for the single megahertz range. My preferred, I mean, since I love brown dwarfs, so my preferred range is the gigahertz range. But if we want to have that full picture, we really need several orders of magnitude of frequencies.
Thank you.
Great, so we have the speakers come up for a quick discussion. I think, thanks, Melody. I think that's a perfect example of the Kavli Foundation support for this session is to bring some speakers in that wouldn't normally come to AGU, both so we can hear some excellent science, but so they can also hear some excellent science here at AGU. There's, for those, while people are getting settled, there'll be a parallel session for people coming to the American Astronomical Society meeting in a few weeks that actually Cayman will be speaking at, along with John Lenine and a few others. So if you're going to be at that session, we hope to see you, or at that meeting, we hope to see you here. Sure.
So we quickly designed this panel discussion. We only have about 15 minutes, so we thought it would be best to ask each of the panelists the exact same question and hear their different takes on it. And if we have time at the end, we'll take some questions from the audience as well. And so the question, as I was scribbling during all of the talks, came out to be something along the lines of, and we can start with George. So in each of your talks, you outlined what is important, what's going on in your field right now. And this is, of course, frontiers and exoplanets, and particularly since it's a joint AAS AGU session. What are the questions that we should be that we can answer that can only be answered by having the geoscientists and astronomers working together? We have astronomers on the panel. What would you like from geoscience? And we have planetary scientists who would like to know what they can get from astronomy. And so, yeah, George, go ahead.
Well, I think the picture that I would see for how we would better use the test data from the first extended mission and hopefully the second extended mission is the knowledge that we actually will be able to penetrate into what are more traditionally thought of as habitable zone planets, and and as a result of the fact that we are looking at the solar neighborhood, the brightness of the host star means that you're going to be able to do things with, in terms of observations, with a 10-meter telescope that otherwise it might require a 100-meter telescope. And so I would think that for certainly for theory, as well as for simulations, that to look at the kind of things that you'd like to have in terms of things like polarimetry and modeling. I don't think we're going to be able to help much on this in terms of surface physics or anything like that, but certainly for starting to do atmospheric physics in a much more quantitative way. The database that I think Tess will provide will actually be very helpful. One of the objects that was described today was LH3844, and that was in fact one of the first discoveries that Tess actually made. And I think there's going to be a whole lot more of those, and looking at these phases between the bright spots, how far displaced they are from local noon. Those are questions that are going to be important to resolve. And I think that the quality of the data that will be obtained in the ground-based follow-up work is going to be critical to really understanding the 10,000 plus planets that we expect will come out from the extended surveys.
Thanks, George. Stephen?
So as I mentioned in my talk, or implied at least, one of the main differences between exoplanets and the solar system is that when it comes to exoplanets, we only get as far as the atmosphere. For a solar system, we can look at atmospheric and in situ surface processes at the same time and see how they're directly affecting each other. We can't do that for exoplanets. And what that means is that for exoplanets, when we're inferring that from the atmosphere, we're going to be using models based on solar system data. And so it's important to get that part right. And so with the question about how the disciplines like geophysics are going to be contributing to this, it's going to be all these processes that contribute to what has influenced the evolution of the atmosphere, since that is our measurable from exoplanets. Things like outgassing in particular, the degassing of a planet as a function of age and mass of the planet, with all the results we're going to get from tests to be able to bring this statistical hammer down on that kind of a problem is going to be amazing, but it's going to be in the context of models from solar system data that have been used to make that inference complete.
Great. Jacob?
So, Stephen, you just sort of stole my thunder there. I was going to say
go plus one.
Outgassing is sort of the process, the lower boundary condition to the sort of atmospheric escape that's happening at the top of the atmosphere that we're pretty sure is happening for these highly irradiated terrestrial exoplanets in the habitable zone or interior to the habitable zone around M dwarfs. We know there that the atmospheric escape is happening, and so whether or not they have atmospheres it sort of depends on how much outgassing is going on. So that's going to be really important and definitely a region of crossover between the statistics and data provided from the exoplanets and what we can learn from geophysicists in the study of solar system objects. But then I'd also just like to second Sarah's plea to the laboratory measurement community. I'm probably stealing your thunder now, but I think it's important
I
just
wasn't going to talk about lab measurements, so you're fine.
just the optical constants for gases and aerosols across broad ranges of temperatures and pressures are fundamental to interpreting the data that we get. So I really support those types of measurements.
Sarah?
So I think some of the most impactful conversations I've had over the past year or two in terms of thinking about exoplanets have actually come in conversation with people who study the early Earth. And I think one of the things that gets lost in some of these conversations is that, the state that the Earth is in now in terms of its atmospheric composition is not the state that it was in for most of its history. And so, if we're talking about the average state that a planet has been in over its lifetime, most of the solar system planets are not actually in that state at this point, and Earth is a particularly extreme example because of how much life has modified its atmosphere. And so I think one of the things that we really have to think about if we're thinking about the search for life is that life has existed on Earth for a very long time. But what did its atmosphere look like during that period before the life on Earth was really strongly modifying the atmosphere? And the other reason I have found those conversations to be really impactful on my thinking is that studying the early Earth is kind of similar to studying solar system planets or to studying exoplanets in the sense that most of the information is gone or inaccessible to us. And so you have to be very clever and creative about the ways in which you figure out what the conditions were like during that period of time. And so in that sense, I'm really looking forward to more collaborations going forward with people who are thinking really hard about, earlier periods of Earth's history, because I think they have a lot of tools and insights that will be useful, both for studying solar system bodies now, but also for studying exoplanets going forward.
Great. Melanie?
So I started my PhD by studying Dynamo papers from Dwarfs, and these are basically stellar objects around which many terrestrial planets are found. But Dwarfs are also somewhere midway between in the Dwarf spectral ranges when we start to see more planetary dynamo-like behavior begin to emerge as objects turn into brown dwarfs. And now I actually try to read a fair number of planetary dynamo papers. But one of the things that can be challenging for me is that we don't have the same detailed observations as what planetary scientists have. And so there are these extraordinarily exquisite models of, for instance, Jupiter's magnetic field, and then I'm sitting there thinking about, okay, if I'm observing this thing from really far away, then what might that tell me? And that's just one object. Dynamos are not deterministic systems at all. They can be quite chaotic. And so what I would really love to have more of is them to take the skills that have been really cultivated in the planetary community for modeling these dynamos in our solar system and applying them to brown dwarf parameters. So for instance, with these new observations suggesting that the Jovian core might actually be dissolving into its metallic hydrogen region. What happens if you take that core out and you're left with a brown dwarf? And then when you're modeling these dynamos, then also if it's possible to pretend to observe these far away and tell me what are observables that I as an astronomer can measure. So things like surface average magnetic fields instead of the complex magnetic fields, surface average magnetic fields, maximum surface field strengths, the time-changing behavior, simulations of objects that have steeper density gradients than what exists in planetary simulations. These are all parameters that are more applicable to me, but the reason why you guys should care about it is because I can give you many, many objects to test the same physics that you're putting into your simulations. The fluid dynamics is all very similar. It's just the parameters are different. So if you give me your simulations, I can test them with objects that are above and beyond what we currently see in our solar system.
Great. That's a great kind of wrap up to what all of you talked about, which is these close connections and growing connections between the fields. So it is a little after 12:20. I want to give people a chance. There is actually an astrophysics Frontiers lecture today by Brent Tully, not on exoplanets, so I might mention some of them, but it's more on kind of cosmic structure, which is also, we're trying to bring some new science into AGU. Jim Head, I will let you ask one quick question if it's quick.
It's quick, just a quick statement. Jim,
Since we do have a Venus expert in it.
I just wanted to say that you shouldn't feel so bad about all these unknowns that you have here. It's like, I think I would just say that it reminds me of what Einstein said at the advent of the nuclear age, which is everything's changed by our way of thinking. What it's done for us, okay? So you incredibly enlarge the parameter space, which is so exciting because we're thinking, oh, okay, look, this is the way it works. But this is a really poor solar system we've got here. That means it really challenged us, and we just got to keep talking together. You know, we're going to work on Venus. It's just incredible. So don't feel, press on with what you're doing because it's the future for sure.
And what's really exciting is we're going to have, we're at that really cusp of a data revolution in both planetary science, because as we saw, some of these stellar telescopes are actually telling us a lot more about the solar system too. So it's great. Thank you all very much. Thanks for coming. Thanks, Chris, who's here from the Kavli Foundation, and the Kavli Foundation for supporting this. Thank you all.